All right. Um, Thank you. Okay. Sorry, that took a while. So, aside from the slightly, including molarity, finding like concentration of ions left over, that's about the level that you'll see for stoichiometry on the exam. So hopefully nothing too impossible. They do take time until you're good at them and then you zip through them, but it takes a while. So this is our last lecture. You guys are welcome to come tomorrow if you can make it to the review in person, but you can also watch it recorded. So I'll just be going over the practice exam. It is in the same folder as all the other practice exams. And I think the key is there too. So let's just finish this last section. We're going to talk more about thermodynamics. Oh, yeah. Go ahead. Same time, 1 o'clock, 1 to 3, and it's in this room. All right. And you can actually watch it live at home if you don't want to drive. The YouTube link, like when I stream, it streams live. I think there's an 8-second delay, but that's it. So I just won't. There is a YouTube chat. I can't see it. I don't have time to look at it. So if you try to ask questions, text somebody here. If you know anybody. Okay. So this is a little bit related to what we did in lab today. This is a very typical combination of stoichiometry and energy, heat enthalpy transfer. So how much heat is absorbed when 25 grams of ammonia reacts in the presence of excess oxygen to produce NO and H2O according to the chemical equation? I think some of you saw the answer, so I'm just going to work on it. So this is basically stoichiometry, except instead of using a mole to mole ratio, you'll use an enthalpy to mole ratio, which is what kind of every time you guys were doing the delta, the heat per mole, that's kind of what we're building here. So 25 grams of ammonia. To convert that into energy, I need to turn that into moles first. Anytime you work with these reactions, they'll also be in moles. The molar mass of ammonia is about 17.02, something like that, maybe 1.3. It's close enough. So this will give me moles of ammonia. The grams will cancel. And then I'm going to use a mole ratio, but not exactly a mole ratio. So moles of ammonia is going to be in the denominator to cancel out. But in the numerator, I'm going to have energy, because that's what I want to calculate. And this ratio is literally the enthalpy 1168 for every 4 moles of ammonia. That's what the stoichiometry tells me. And so this is the math. Moles of ammonia will cancel out. Kilojoules is going to be our answer. And so for that specific amount of ammonia, just like we had specific amounts of sodium hydroxide and all that in lab today, that specific amount will generate 428.6 kilojoules of energy. Okay? Or not generate, excuse me. It's positive, so it'll absorb. I keep saying that wrong. This is an endothermic process because it's positive, so it's absorbed, not released. Excuse me. Okay. So hopefully this is not too difficult. This is just an extension of stoichiometry. What we're going to focus on now is how to calculate that delta H. And so we spent a lot of time doing it with calorimetry. We did that in the lab. Q is equal to MC delta T. So don't forget, even though this equation gives you Q, Q is equal to delta H when your reaction is run at constant pressure. That little subscript P is just a reminder that we're measuring the heat transfer under constant pressure conditions, which is almost every reaction we do in the lab, because constant pressure is our atmospheric pressure. So that's the shortcut we take, and so that's why we can quickly calculate the delta H. We usually want our delta H per mole, so we just have to make a slight adjustment. We make it per mole instead of just for any random amount. But that's one way to get delta H, is through calorimetry. The other way to do it is we can calculate it, and there's actually 4 ways. So the second way we're going to do it is to calculate delta H from standard enthalpy hey, this is the delta H for this particular reaction, this is the delta H for this particular reaction. And we've got this big, giant repository of delta H's. Now, there are specific kind of reactions we have stored, delta H's for. So we're going to skip this one. This is Chem-Activity 2032, I think. We're going to skip that. It's something called atom combination. And the idea, and we're not going to get into this real quick, but the idea is we're looking at how to make different compounds from their atoms. And I don't know if this is as common as the next one. I'm pretty sure it's not as common because I had never heard of this until I started teaching here. So we're going to skip this one. We don't have time for it. What we're going to do is look at formation reactions instead, not atom combination. So what is a formation reaction? Right, that is a different idea. So a formation reaction is defined as how to make 1 mole of a certain substance. So you pick whatever you're trying to make from elements, and elements in their standard states. So this word standard, we've heard this before, but it's a different version of standard. So in gas laws, standard was 0 degrees C and 1 atmosphere pressure. That's not the same in thermodynamics. In thermodynamics, standard means 25 degrees C, which is kind of warm, actually, but it's considered room temperature, and 1 atmosphere. So you'll often see, well, we'll show you that in a second. So if I were to say, well, what is this formation reaction for calcium carbonate? Well, the idea is we want to write a reaction that shows how to make 1 mole of this from elements. And so the elements form of calcium is just calcium metal. The element form of graphite, well, there's many allotropes of carbon. There's diamond, there's buckyballs, there's graphite. We're looking for the one that exists normally at 25 degrees C and 1 atmosphere pressure, and that's graphite. So that's the elemental form of carbon under standard conditions. And oxygen, it's not O, doesn't exist as 1 oxygen. Oxygen is a diatomic molecule under normal conditions, so it's O2. And these 3 elements combine to make the product that we're looking for, calcium carbonate. And again, the restriction is we're making 1 mole of this substance. So we have to have a coefficient of 1 on the product. And this is where you have to start looking at fractions, because normally we'd write this as 2, 3, 2, 2, so that there's no fractions. You can't do that for formation reactions. It has to be to 1. So that's what a formation reaction looks like. And so we've got this giant table of formation reactions. So you can look them up by the compound, and you can look up, well, what's the delta H for that reaction? And this is just a small part of it. So here are formation values. Notice that instead of writing the generic delta H subscript RxN for reaction, we're more specific. It's a formation type reaction, so with a little F there. It's just a label, that's all it is. And that little degree symbol that's next to the delta H up here is indicating standard conditions. So these are all measured under standard conditions. So 25 degrees C, 1 atmosphere pressure. Thermodynamics is pretty complicated, and it gets more complicated when you start using different temperatures and different pressures. So we're going to keep all these the same. Now notice there's a lot of zeros in here. And that's because think about what a formation reaction would look like for something like F2. So the formation reaction for F2, how do you make F2 from its elements? Well, the only element in there is fluorine, and the elemental form of fluorine is F2. There's nothing happening here. And that's why the delta H of this formation reaction is 0. So any element that's in this table has a delta H formation of 0. Because it's already, you can't make an element from its elements. Nothing's happening. But something like diamond, that's not the elemental form of carbon, which is why when you write, how do you make diamond? What's the formation reaction for diamond? It's going to be, well, you're making it from graphite. So there's a change happening there. And the delta H for this reaction is, according to this thing, 1.88 kilojoules per mole. It's endothermic. You have to put energy into it to make diamond. That makes sense. Okay, so that's what these formation reactions are. Notice the state matters quite a bit. Gas water versus liquid water, they have different values because it takes more. You get more energy out of it from making liquid water than gas water because the gas water retains more energy, right? Because it's in gas form. So phases matter. Make sure you look at those. Here I can show you real quick. If you want to see a giant list of these things, besides the internet, you can probably find them on the internet. If you look in your textbook, under Mastering Chemistry, and there might be some in the back of the workbook too. I'm not sure. God, there's so many steps. Hold on a second. The laptop's checking. So many steps. In my class yesterday, some people were like, "I've never been to the textbook," and I don't blame them. It's a lot of steps to get to it. All right. We don't use it that much. It's more of a reference text. So once it loads, come on. Yeah. So you have the paper one? Okay. So if you go to table of contents, I'm already here, but if you go to the table of contents, and then you go all the way down to back matter, appendix 2. This is where it all is. And we'll skip the atomic colors because this is not really what they look like. This is just a standardized color for when you illustrate things. But here, B. This is a really long table. And all we're interested in is this column here, delta H of formation. You'll learn this in 220. Yeah. So you look it up, and I don't know if you want to see, but it just keeps going. There's a lot of stuff on here. And this isn't even a very long list. I mean, there's millions of them. Oh, there we go. Stop there. So, delta H is a formation. All right. You don't have to memorize any of these other than knowing elemental forms already have or delta H of 0. Okay. So for instance, on an exam, I would give you a list of the ones you need, and then you might be like, well, this one's missing. Why is this one missing? Well, maybe it's an element, and you should know that it's got a delta H of 0. Okay. So which one of these is not in its standard state? Why isn't the clicker thing working? Did it crash? Oh no, it didn't. I just didn't start it. Nope, wrong one. There we go. Oh, I don't know why the timer turned on. All right. There's a few clicker questions. So. All right. Okay. So hopefully this one's not hard. So we've got most people voting B. So this is going back to intro chem. You gotta remember that a lot of these elements are diatomic naturally. So hydrogen is, and then if you start with nitrogen, oxygen, fluorine, and then you go down. Chlorine, bromine, iodine, they're all naturally diatomic. Mnemonic too, if you like, have those here at high school beer. The first letter in each word, or first 2 letters in each word, remind you of the elements that are naturally diatomic. So in addition to the formula being right, make sure the state that it's in is right. So bromine, so whoever selected this one, maybe they saw the liquid part. Bromine actually is a liquid at room temperature. Iodine is a solid at room temperature. The rest of them are gases, though. The chlorine, the fluorine, the oxygen, and nitrogen. So, yeah. Uh-huh. That's fine. If I said gas, it's a gas. It's as long as it's Br2. Yeah, okay, you're fine. So all that meant was we ran the reaction at a slightly higher temperature than room temperature. That's okay. Wow. I don't know what I was thinking. Okay. So what do we do with these delta H's of formation? So we've got all these delta H's of formation, they're very limiting, like we're only looking at a certain kind of reaction. So what are they good for? So by the way, here's just some extra, we just looked at calcium carbonate. The delta H of this reaction is minus 1208 kilojoules per mole. Again, you don't have to memorize any of these numbers. Here's a different compound with calcium oxide. Formation reaction has a delta H of this. Here is carbon dioxide. So these are all involving oxygen. These are all actually kind of, well, they're not exactly combustion, but they're combustion-like. It's just examples. That's all they are. And this is typically how they're written. A delta H of formation, and then maybe you'll have in parentheses or a subscript also the identity of the substance it's referring to. So making CO2 as a gas. So you'll see that a lot. Delta H of formation of oxygen. So we did fluorine, but delta H of formation of oxygen is 0 because that's the standard state of oxygen. You're making O2 from O2, which is nothing's happening. So there's no energy required. Okay. I mentioned this one. Here's graphite going to diamond, which is right over there. The delta HF is 1.895 kilojoules per mole. Okay. And even atomic chlorine. So what is the delta H of formation of atomic chlorine? Well, the standard state of chlorine is Cl2. So if I take half a mole of Cl2, I can make a mole of Cl atoms. And that actually takes energy. You have to add energy to break that bond. So anyway, these are just examples of formation reactions. And so this is what we do with them. This is why they're useful. I can calculate the enthalpy of any reaction, not just a formation reaction, but any reaction, if I examine the reactants and products and write down their formation reaction values. And I will have to basically sum, this is what that means, this is the sum of the delta H of formation of all of the products multiplied by the number of moles, so the coefficient in front. And then I can subtract the sum of all of the delta H of formation reactants times the number of their moles. So let me show you how this works. Well, first, this lets us calculate, again, the delta H of any reaction. And you might think that that's like, we can calculate anything. Well, you're limited because delta H of formation reactions are all measured at 25 degrees in 1 atmosphere. We're also limited by the 25 degrees in 1 atmosphere. So the delta H for any reaction we want is only going to be the delta H at that temperature and pressure, okay? So there's a small limitation, but that's all. So let me show you how this thing works. So what if I wanted to calculate the delta H of reaction for this reaction? What is delta H is equal to what for this thing? So this is not a formation reaction. This is just a regular reaction. So we would just write the generic delta H RXN. What I would do is I would go ahead and look up all of these values. So this is how I do it. I'm going to write down this equation. Over here, C4H10 is a gas. 13 over 2 O2 is a gas. 5 H2O is a gas, not a liquid. So it's important you know which one's CO2 is a gas. And before I jump to the table doesn't have C4H10, so I'm going to cheat and look it up real quick. It's so 3. So if I go ahead and look up all of the delta H's of formations, this one is going to be minus 124.73 kilojoules per mole. And I'm going to look up all of them. So I'm going to go back to the table. And yeah, the C2 or C4H10 is not in there, but if you could look it up in another table. H2O as a gas is minus 241.8. And then CO2 as a gas is minus 393.5. I don't even have to look up O2. I mean, you can, but it's an element, so it's going to have a delta H information of 0. So I like to organize my data so I know what number belongs to what. Now, the math here is going to be the sum of all the products minus the sum of all the reactants. And so the math goes like this. The first product is water. There's 5 moles of water. Right, that's the coefficient in front. And the delta H of formation value is 241.8. And the units are kilojoules per mole. So you can see that moles will cancel and you're left with just kilojoules. And I'll add the next product. The next product is carbon dioxide. 4 moles times minus 393.5 kilojoules per mole. And that's all the products. And now we're going to subtract all of the reactants. Now I'm going to put this in brackets because this minus applies to all of the reactants. So if you have more than one, or more than one that actually have values in them, you'll distribute that minus to all the terms, okay? So in this case, we've got 1 mole of butane, and it's got minus 124.73 kilojoules per mole. And we also have oxygen. I mean, I'll write it, but you can see that even though it's 13 over 2 moles, it's 0 kilojoules per mole. So that's going to go away because multiplying by 0 makes it 0. Oh, sorry, I didn't even put minus, plus. So this minus will make this whole thing minus and this whole thing minus, although that minus will cancel out. So there's a lot of mistakes to be made with algebra, so make sure you carefully distribute your minuses where it makes sense. And then when you solve this, I'm not even going to do it because it's in the slides. When you solve this, you end up with minus 2,658 kilojoules per mole. So that is the delta H for this reaction. Right? So when you write the reaction, and there's a delta, what is the delta H of reaction for this thing? It's going to be minus 2,658 kilojoules. And this says per molar reaction. So the idea is per mole of butane, per 5 moles of H2O, per 4 moles of CO2. It depends on what you're referring to, but that's the delta H. Okay, this works pretty well, actually. This, I think, is compared to a different calculation that we're not going to do. And it agrees pretty well. It's not perfect, but it works similarly. And in fact, it works pretty well with compared to calorimetry. So this method works really well. So delta H's of formation is extremely useful, and you'll get a table of whatever you need if you had a question on the exam. So again, we'll give you the relevant ones, and if you don't see something you need, maybe it's an element. It's probably not. It could be my mistake, but usually it's because it's an element. You should know it's 0. Okay. All right. So I think we're going to skip this because we're going to run out of time if we try to do this. But these are practice problems for this kind of thing. And once you've seen one of these and done one of these, it's pretty easy. The only other variation of this problem you'll get is, I think it's the next one. Yeah, here we go. So let's try this one. We have a reaction. and I'm telling you what the delta H of the reaction is already. But I want you to calculate the delta H of formation of nitrogen monoxide. So NO, given that the delta H of formation of NO2 is 33.9. So basically you're kind of going backwards a little bit. Let's see if you guys can do that one. So set this up, products minus reactants is equal to delta H reaction. Plug in what you know. The thing that's missing, you can make it a variable and solve for it. Again, that's capital sigma. In math, that means sum of. That's all. Oh, ran out of time. I hate this timer thing. I don't know why it suddenly showed up. Sorry, the timer's on. If you have your answer, it's fine. The people that voted, well, 50-50. So the answer is, come on, is B. So how did we get that? It's the reaction itself, the whole reaction is minus 114.14. And the product's just one, there's NO2, and we know the delta H of formation of NO2, it's 33.9. And we're multiplying that by 1 mole. There's only one coefficient of 1 in front of the NO2. And we're going to subtract all of the reactants. So we can ignore that one because that one's 0. NO is the one we're looking for. And there's just 1 mole of it. But this is the one that we're looking for. We're looking for the delta H formation of NO. So really it's just algebra at this point. You subtract this from both sides, and then you get rid of the negatives, and you end up with a positive 148 kilojoules. So that's the delta H of formation of NO. NO is actually a very, very famous molecule. Scientists won the Nobel Prize for it in chemistry because ultimately their research led to the production of things like Viagra and Cialis. So NO is a big part of the vasodilation, I think, mechanism, or constriction, maybe the other way. I'm not a bio person, so anyway, so that is delta H of formation. I think it's really, really easy to do. I think once you've done it once, you're like, this is not too bad. We'll give you all the numbers. You just have to plug them in and solve for something. So, and like I said, there's like, well, I shouldn't say I should have said there's millions, but we have tables and tables of delta H's of formation. We don't have everything. So what if it's not in the list? What do we do? And you can ignore this part. But what if we don't have the delta H formation of something, and we want to calculate a delta H anyway? And I don't want to go in the lab and measure it. Maybe it's hard to measure. Well, we can do something else. We can use something called bond dissociation energies. So this is a third way to calculate a delta H of reaction. And so first, let's talk about what a bond dissociation energy is. We're going to use the variable D. You're going to see that as, hey, D is equal to this. That literally means the bond dissociation energy, how much energy it takes to break the bond. So for instance, if I were to say that chlorine has a D is equal to 243, that's the bond dissociation energy for a chlorine-chlorine single bond. Literally, that means I'm taking chlorine gas and turning it into 2 chlorine atoms, breaking the bond. And that particular reaction has a delta H of 243 kilojoules per mole. That means those two mean the same thing, okay? So bond dissociation energy, that's literally what it means as an enthalpy, okay? Dissociation energies are always positive, and you know this, even though you don't realize it, because when you make a bond, the whole point of making a bond is to lower the energy of your molecule. So Coulomb's law, when two ions that are opposite charge come close together, their potential energy goes down. So to bring them back apart, you have to add energy to it to break them back apart, okay? So always positive, because you're breaking, you have to add energy to break it. It's endothermic. So here is a table of bond energies. And what's important to note is that these are not exact. These are averages. And that's because if I look at, for instance, a CH bond, which is 413 kilojoules per mole, well, do you think that maybe the hydrogen-carbon-hydrogen bond on the end of a molecule might be different than the carbon-hydrogen bond inside a molecule? Yeah, they could be different. And so what these are just averages. They measure a whole bunch of different kinds of carbon-hydrogen bonds, and they probably calculate, well, how frequently does that occur? And then this is an average. So let's just accept these as an average. The only, so we have single bonds, we have double bonds, and we have triple bonds. O2 here actually has a double bond, and you'll have to do a Lewis structure to realize that. But it has a double bond. The only distinction, at least in this table, is for most C double bond O bonds, like on a ketone or an aldehyde or an acid, that's the bond energy, 745. But if we're doing CO2, which also has CO double bonds, we're going to use a slightly different number, 799. So that's the only distinction we're making between, hey, this bond is different from this molecule. So that's it. So what do we do with these? All right. So let's say we have this reaction. And I'm going to do it on the board because I like it explained on the board better. What you should be doing, and you can take shortcuts once you're getting good at this, but what you should be doing is drawing out every single reactant and product. And it will help you a lot. So for H2, what does H2 look like? Pretty simple. Single bond between two hydrogens. But in addition to drawing out the molecules, draw out the correct number of molecules. So the coefficient 2 means there's 2 hydrogen molecules. So I'm going to draw 2 of them. And this is reacting with O2. And if you do the Lewis structure, you'll find that O2 has a double bond between it. And you can, if you want, you can do the lone pair. That's not necessary. And this turns into two waters. So what does water look like? Looks like that. And there's 2 of them. So the reason it's a good idea to draw them out is because you have to count all the bonds. Red. So we're going to start with on the reactant side. So the way to think about this is for these to turn into this product, I'm going to have to break some bonds first, right? And then once I break the bonds, I'll have to make new bonds to make the products. So you could be picky if you want, but the easiest way to do this is to break all the bonds. Break all the bonds on the reactant side. So how many hydrogen-hydrogen bonds are we going to make? One. This is dead. Nice. How many hydrogen-hydrogen bonds are we going to break? We're going to break 1, 2. So I'm going to write down 2 hydrogen-hydrogen bonds. All right, what else? We're going to break an oxygen-oxygen double bond. Just one. So I'm going to write down 1 oxygen-oxygen double bond. And then we're going to make some bonds on this side. And so well, how many bonds are we going to make? Well, we're going to make 1, 2, 3, 4. 1, 2, 3, 4 oxygen-hydrogen single bonds. So I'm just keeping track of all the bonds I'm breaking and all the bonds I'm making. So if they're on the reactant side, I'm breaking the bonds. If they're on the product side, I am counting all the bonds I have to make. All right, so this is break these. Make these. Anyway, so this is where we go back to the table. And I will look up what does it cost to break an HH bond. 432 kilojoules. What does it cost to break an O2 bond? 498. What does it cost to break? And even though I'm making them, what is it? These are all breaking. What does it cost to break an OH bond? There it is, 467. So I'm going to sum up, and I'm going to put a little dividing line between them. I'm going to add up all of this. So there's 2 times 432. And then there is 1, 498. The total amount of energy I'm going to spend breaking bonds is 2 times 432 plus 498 is 1362 kilojoules. On this side, ignore the fact that I'm making them. Let's just add up all the energy here. So it's 4 times 467. That is 1868. So remember our properties of enthalpy. These are all bond breaking. What do you think the values would be if I'm making the bond? Just negative, yeah, exactly the same, just opposite. So this one right here, this is all, if I was breaking 4 OH bonds, that's how much energy would cost. If I was making them, it would be the opposite sign. So the shortcut here is we're going to do the reactant energy minus, that's how we make this one negative, minus the product energy. So 1362 minus 1868, and that's going to give me negative 506 kilojoules. So that right there is the delta H for that reaction. For this reaction that, here, I'll go back to the page. This reaction, that's the delta H for that reaction. Now, it is not as good as, first of all, measuring it directly in the lab. That's always the best. It's not as good as a delta H formation. And that's because these are average bond energies we're using. So they could be slightly different in real life. From the actual bonds we're breaking and making might be slightly different energies. So if you look at, hold on a second. They used a different table than I did, so they got a slightly different number. But if you use a delta H formation method, you'll get minus 484 kilojoules. So that's a little different. But it gives you a good idea. So it's better than nothing. Yes?
How come on that side we use, when we had O2, we marked it as 0, and then on this side, I guess it's got 4.
formation reaction is a very specific reaction. How do you make that product, O2, from its elements? It's O2 to O2, nothing's happening. But with bond dissociation energies, you're just saying, what does it cost to break that bond? And it does cost energy. So it's a different concept. Remember, enthalpy is a state function. We can calculate enthalpy from lots of different pathways. So these are just different ways to do it, but they're all going to get approximately the same result. Not perfect here, but close. So why don't you guys try one on page, well, I don't know what page this is. Chem activity 33A, question 7. I want to make sure this makes sense to you guys. If anybody knows the page, yell it out, please. You're right there. There you go. 184, okay. Sounds good, thank you. Number 7. So this one's set up already where everything's drawn out, but you'll often see them where you have to draw it yourself. Okay. Because the reason why it's all drawn out, it's a good way to see it. The common mistake is they see C3H8 and they're like, oh, I'm breaking 3 carbon-carbon bonds. No, 2. You can see that when you draw it out. Okay. More than 6.
Wait, say, can you say that again? You said we're breaking only 2 bonds for this one?
So a common mistake people make is they don't draw it out. They're like, oh, I'm breaking 3 carbon-carbon bonds.
Oh,
But it's actually just 2. But and then 8 carbon-carbon.
yeah, okay.
Very, very common mistake. It might be listed as O2 plane. Where is it? There it is, O2.
Oh,
Can you show us the amounts breaking up?
They're on the previous page.
There you go.
Yeah, so these values that in the table are also something you shouldn't have to memorize. Don't worry. You'll get a table if you need it. Okay. Yeah, 5 bonds. Yeah. 5 O double bonds.
This is not LL.
Yeah, this often happens. I don't know why they do that. Everything else is written out explicitly. That one's just O2. It might be because O2 is technically not double bond when you measure it in real life. Even though we drop it. O2 is complicated. Very complicated. In fact, there's a whole grad level course devoted to O2 because it does weird things in your body. Even though you need it to live, it's also the thing that killed you. Yeah. Oxidative damage. Yeah. work well in a petri dish, so it's not so much the same in your body. In vivo versus in vitro. And notice that this is different from the formation reaction. In the formation, we did products minus reactants. With bond association, it's the reactants minus the products. Right? So it's the opposite. Bonds broken at the reactant side minus bonds formed at the product side. So don't get confused. They're opposite. Yeah, most atoms like 8 electrons. There's some exceptions, but yeah, most of the main components definitely like 8 electrons. Yeah, so that's a different thing, but yeah, oxygen will often have 2 bonds, whether it's a double bond or 2 single bonds, 2 bonds. And it's kind of a pattern. The halogens use 1 bond, the fluorine and everything. Oxygen has 2, nitrogen has 3, carbon has 4. That's the common number of bonds. You can always break that rule. There's ways around those. Okay. How are we doing? You got a number? Big negative number, right? Okay. Negative 2,000 something. Okay. Something like that. Okay. So this is not hard. I mean, because it's set up for you, but you're going to have to learn how to draw it out yourself when you get to that. So that's number 3. That's the third way to do delta H's of reaction. Now the last one, Hess's law. We did this in the lab. So again, let me kind of reintroduce Hess's law. This is the idea that you can combine multiple reactions into a new reaction. And you can determine the new delta H's from the original delta, like the reactions of that you combine from the delta H's of those reactions. So here's 2 reactions. I've got carbon turning into carbon monoxide, has that enthalpy. I've got carbon monoxide turning into carbon dioxide, that has that enthalpy. Well, what if I wanted to look at carbon turning into carbon dioxide directly? Well, that's just these 2 reactions added together. You notice that the CO and the CO cancel. The O2, half O2 and half O2 add up to 1 O2. And the delta H's add together. And that is the delta H of this new reaction. So that's the basis of Hess's law. And again, this works because you can calculate a delta H any pathway you want, as long as you start with the right reactants and the right products. I mean, so that's what we're doing here. We're starting with reactants, going to the right products, same thing. Okay. So we saw in the lab how Hess's law works, and how it's, it really does work. And we did one example problem on the board. Let's do a couple others. So here's, and this is just a visual that goes along with that reaction that was just on the board. The reactants carbon and oxygen have a lot of energy. When you make carbon monoxide, it releases energy because the products have lower energy than the reactants do. In the second reaction, it releases more energy, but if you go straight from these starting materials to these products, It's just those two together, and you can see that they literally do add up to minus 393 kilojoules. All right. So somebody was asking about, well, how useful is this? Well, here's a real example. How would you calculate C60 going to diamond? Because I don't know how easy that's to do. I don't think that's easy to do in the lab at all. But if you could do it, what would the delta H be? Well, since I can't really calculate it in the lab, it's hard to do that reaction. Why don't I look at burning C60 to make CO2, and then burning diamond to make CO2, and those are the respective enthalpies. They are exothermic. You're burning something. How would I put these two together? Well, let me erase a second. Again, be methodical about it. Start with one reactant at a time. So I want to start building my equation. I need to have 1/60th C60 on the reactant side. It's right there. It's the only place it is. As written. 1/60th C60. Plus an O2 goes to CO2. I'm going to leave the states off because in this particular example it won't matter. Minus 435. So next I'm going to add the equation of obviously the other one that exists, but how am I going to add it? Well, I want diamonds on the product side. Here are the diamonds on the reactant side. So let's reverse the reaction. If I reverse it, it's CO2 goes to C diamond plus O2. And when I reverse the reaction, the delta H is reversed as well, or take the opposite sign. Positive 396 kilojoules. And then I'll combine these two equations together. C60, well, let's just cancel out what doesn't belong. So I'm going to have a CO2 on the product side and a CO2 on the reactant side. Those will cancel. I have an O2 on the reactant side and an O2 on the product side. Those will cancel. And what's left is, hey, exactly what I'm looking for. C60 going to C diamond. And the delta H for this weird reaction that I probably can't do in real life because it's difficult. If I could do it, would be minus 39 kilojoules. So this would actually release some energy. Why would we need to know that? I mean, who knows? It's pretty interesting that there is more energy stored in C60 than there is in diamond. Because making diamond would release energy. So diamond stores less energy. And diamond is actually in a lower energy state than C60. So, okay. That is a simple example. You'll see this on the exam definitely. Something like this. This is a very common one. Here's the worked out problem in case you missed it. So what about this one? That line there is, I don't know why it's there. It shouldn't be exactly there. But I've got an unknown reaction. 2H2 plus N2 goes to N2H4. And I want to know the delta H for this thing. But I've got some known reactions. We have N2H4 and H2 go to ammonia. And I've got hydrogen and nitrogen go to ammonia. How are those going to combine to make the first reaction? So here's how I'd start. I'd start from the beginning. I'm trying to build up this reaction here. And the first reactant is hydrogen, H2. Now, when I look for H2 in the known reactions, it's actually in two different places. It's there and it's there. So which one do I use to start my reaction? I have no idea. So let's skip hydrogen. We can come back to it. So let's skip hydrogen. Let's go to nitrogen. And that was easier because the only known reaction that has nitrogen in it is this one. So I'm going to start with this equation because it has nitrogen where I want it. And it's pretty clear that that's the one that I use for nitrogen. So I'll write it, and it's on the reactant side. There's one nitrogen, one mole of delta H is minus 92.2. Okay, again, I could go back to hydrogen, but why? I'll just keep going. Let's add N2H4. So I want N2H4 to be on my product side. And the only reaction it occurs in is this one. And it's on the wrong side, it's on the reactant side. So I'm going to reverse it. So I'm going to write that second reaction reversed. 2 ammonias goes to N2H4 and H2. So reversed, it's positive 187.6. And now I'm going to combine these two, because I can't have two reactions, I need one. I'll just do some pre-cancellation to make things easy to write. You can see that ammonia occurs in both reactions, one on the product side, or two on the product side, excuse me, and two on the reactant side. That's perfect, they'll cancel. And that's it. Oh, actually, there's one difference. So hydrogen also occurs on both sides. Here on the reactant side, here on the product side. Now, we have different coefficients. This is 3, this is 1. If I have two algebraic equations and I'm adding them together, and there's a 3x on one side and an x on the other side, what happens? You subtract x from both sides. So one of the x's is gone, the other one becomes, instead of 3x, it's now 2x. So the same thing happens here. This hydrogen is going to go away, and one of these hydrogens is going to go away as well. So instead of 2, it's going to be, or so instead of 3, it's going to be 2. So when I rewrite the sum, it's going to be 2, sorry, not 3, 2 H2 and N2 goes to N2H4, and the delta H for that is going to be positive 95.4. Is that right? Did I do the math right in my head? I think so.
It's not about.
Yeah, okay. And look, coincidentally, it's exactly the equation I was looking for. So that's that one. So this is, you're just treating chemical equations, and the word equation in that phrase is literally, because it's an equation, we're treating chemical equations as algebraic equations. Yeah.
So to cross out the data, when you're crossing out two vertices, one the ammonia, one was on the product side and one was on the reactant side.
Yeah. So I did it before. So if I don't cross it out ahead of time, okay? If I imagine I didn't cross this out, what I'd be writing is everything on the reactant side. So there'd be 3H2, there'd be an N2, there'd be 2NH3. That's everything on the reactant side. But everything on the product side would be 2NH3, and N2H4, and H2. And then hopefully it's clear, hey, there's a 2NH3 on the reactant side, 2NH3 on the product side.
The original equations, like the NH2 is on the same side, so you have to cross them over to make it so. Like, the NH2 have to be on the side.
Yeah, well, yeah. To cancel them out, they have to be on opposite sides. If they're on the same side, then you would add them together.
Okay, so yeah, so you'll always like swap them so you can cancel them out like that.
So it happened. I mean, it wasn't intentional, but so my intent when I put all these equations together was to make it look like this. Was to make an N2H4 happen on the product side.
Oh, okay.
That was my intent. Coincidentally, I canceled out things I didn't need either.
Oh, okay.
But that is something you can target. So there's two strategies for doing this. One is trying to build the equation you want, and the other strategy is taking out things you don't need.
Okay.
And we'll see that in the next one. Okay. So yeah, this is 2NH3, 2NH3, and then there's H2 and H2. So one of these is gone and one of these is gone. They end up the same. Okay. Now, I tried to make my class yesterday do this, and it took a long time. So maybe we should do this together on the board. but this is a really long one. And so we're trying to find the delta H of this equation at the top, carbon atoms, a carbon atom plus 4 hydrogen atoms make methane. Oh yeah, this is actually a connectivity one. So if you want to look at it in your connectivity, it's 33B, exercise 1. But let's just do it on the board, because I don't think we're gonna run out of time if we do it as a individual. Now, I'll say this. This one's a little bit too long for an exam, because generally when we give you reactions that have delta H's and we tell you use these to build a new equation, you're going to use all of them. So this one's a little bit long. 2 equations or 3 equations, that's probably what I'll use for an exam, okay? But, so first, don't worry about this subscript here. This is the atom combination thing that I told you we skipped. Just treat it like any other reaction. The reaction's right there. It's fine. It's just a delta H, that's it. So what I'm trying to do is I'm trying to build C going to 4 H's makes methane. Yeah. 191. Thank you. Okay. So it's the same strategy. Let's start by building what we need. I need carbon as a gas on the reactant side. And looking through all of these, just to make sure, it only occurs in one spot. That's right there. So I'll write this first. Carbon is a gas, going to carbon graphite, shorten as graph. And that has a delta H of minus 716.682. Okay, so let's add the next thing, hydrogen atoms. And the only place hydrogen atoms occur is right there. So, perfect, it's on the reactant side. I need it on the reactant side. But it's 2 moles. I need 4 moles. So we'll double it. We'll double the entire equation. Yes? It's a special kind of reaction. It's called atom combination. But I wouldn't worry about it. Just pretend it's a regular reaction. Okay. Yeah. It doesn't make any difference. So I want to double this. So if I double it, multiply everything by 2, I'm going to have 4 H's. And that'll make 2 H2s. But if I double the reaction, remember enthalpy is an extensive property. If I double the reaction, I have to double the enthalpy too. So this becomes 870.6. Negative 870.6. All right, so let's merge those two. So we have one reaction. We'll have the carbon gas and the 4 H's on the reactant side. And we'll have the products, carbon graphite, and 2 hydrogen molecules on the product side. My delta H is, let's see, 716.6, and negative 870.6, negative 1587.282. Whatever, we'll cut out some of those digits soon. All right, so it's getting messy, but let's add in the product now. We want to put methane in there. So the only place methane occurs looks like right there. So, but it's on the wrong side. I want it to be on the product side. It's on the reactant side. All right, I need it on the product side. That's where I need it. So let's reverse the reaction. All right. You know what? All right. CO2 and 2H2. Remember, I'm reversing that top reaction. It goes to CH4 and 2O2. And since I reversed the reaction, we're going to reverse the delta H. So it's a positive 802.5. And I'm going to merge this with the previous equation. Add it together. So sorry, I added that one together, and now I'm going to add that one. Let's just write the whole thing. C and gas form, 4 hydrogens, CO2, 2 H2O. Those are all on the reactant side. On the product side, we've got carbon graphite and 2 H2s and CH4 and 2 O2. Sorry, it's getting messy. The delta H is going to be the sum of the previous delta H's. So this one plus now 802.5, and that's going to be negative 784.8. I rounded. Okay, so I've managed to put everything that I want into my equation. I've got carbon as a gas. I've got hydrogen, 4 hydrogen atoms. I've got methane right there. But now I've got a ton of stuff I don't want. So this is the next strategy. Let's try to remove things we don't want. And we'll do that by adding equations in a way that causes them to cancel things out. So I don't want carbon graphite. That doesn't need to be here. So with, oh, and I forgot to do something, did I? No, we're good. I don't want carbon as graphite. So let's see if I can find another equation that has carbon as graphite in it that I haven't used yet. This one. So I've used this one. That was the first thing I used. But this is another equation with graphite in it. So let's use that one. My current equation has graphite in the product side. So if I add an equation that has graphite in the reactant side, they will cancel out. So I'm going to add this thing as is, carbon graphite, plus O2 goes to CO2, and that has a delta H of minus 393.3. And when I do that, I'm going to simplify before I add. So notice carbon graphite on the reactant side, carbon graphite on the product side, those will go away. A few more things do go away as well. CO2 on the product side, CO2 on the reactant side, those will go away. And O2 on the reactant side, 2 O2 on the product side. So some of those will go away. So one of these will go away, and one of these will go away. So that 2 is now 1. I'll put a 1. But we don't have one. Right? So let me rewrite the new addition. Carbon as a gas plus 4 hydrogen atoms plus 2 waters goes to 2 H2 and methane and 1 O2 left. And the delta H for this thing is plus a negative 393.3. 1178.1. Almost there. We still have things we don't want. We don't want any water. We don't want hydrogen. We don't want O2. Well, let's pick the water. So the very last equation we haven't used yet, that third one, we haven't used that one yet. That has water in it. I need something that has 2 waters on the product side so that it'll cancel out my 2 waters on the reactant side. This is close. It's got water on the product side. I just need 2 of them. So let's double this equation. We're going to double it. So double equation number 3, 2 H2s. Double half, it becomes 1, 1 O2. Double H2O becomes 2 H2O. And don't forget, double the enthalpy. So minus 241.8 becomes minus 483.6. Okay, so before I add them, let's cancel what I can. The 2 H2O here will cancel out with the 2 H2O on the product side. The 2 H2 on the reactant side will cancel out with the 2 H2 on the product side here. And the 1 O2 on the reactant side will cancel out with the 1 O2 on this reactant. And now I'm going to rewrite it. The addition up here, I've got carbon as a gas, and 4 hydrogen atoms goes to methane. That's it. What is the delta H? It's these two added together, plus minus 483.6, minus 1661.7. other equations. So, do you have to do this level of complexity? No. But each step that I did is something you should be able to understand. So, knowing when to reverse a reaction and what happens to the delta H, knowing when to multiply an equation by 2 or 3 or any number, you can even divide by 2. If you get too many waters, you can divide by 2 to make it 1 or something like that, or half. Whatever you do to the equation, just like in algebra, you do to the delta H as well. And the two strategies, adding things that you need, taking out things you don't need. Do one thing at a time. And if you come across something, so for instance, well, this one's pretty straightforward, but if you have to put O2 into your equation and you got 3 other equations that have O2 in it, then skip it. You don't know which one you're going to need. So just be methodical about it, and it should be you should get the answer. Be verbose. See how I wrote everything out. And know when you need to use the phases, because sometimes you really need them. If there's a gas water and a liquid water, you'll need to put which one's which. Okay. Finding errors. When you make a mistake, it's only possible to check if you've written everything out very well and neatly. If you don't do that, then I would suggest start over. If you're like, I don't know what I'm doing. I've seen people just kind of just get consumed in what they've done already and they can't see the mistakes. So, yeah. Oh, and we can compare our answers. So, via another method from the formation, it's -1662. We're really close. So, this is a really good method for finding delta H. It's just a lot trickier, that's for sure. In real life, you wouldn't be, like nobody's going to hand you a page of use these reactions. You'd have to look them up yourself. We're not going to do that. That's too hardcore. Okay. I think that's it. Oh, there's one more. We don't have time for it. But feel free to try this one at home. There's an answer. It's like you can skip it. And that's it. That's all we're going to do. So that's the fourth way to find the delta H. We got our calorimetry. We've got our formation reaction enthalpies, and we've got our bond dissociation energies, and then we've got the Hess's law method. Those are the 4 ways we can solve for delta H. Yeah, I'll give you the values you'll need if you need to do that. Okay. That's probably overwhelming, but if you have any questions, feel free. So I'm here around 8:30, and I'll be all morning long. I'll just be grading. And then the last lecture for Thursday's class is 1 o'clock. Okay. So I'll probably be out from like around 11 to just before the class starts, but early in the morning I'll be here. Yeah. If I'm so sometimes I do office hours in the lab, but if I'm not there, check the main office, just knock on the door. One of those 2 places.
Her house kid or dad. So she's gotta wait for her to get home. Because he was in the restaurant, it's like I'm all the way there because she was forgetful. She has to wait like 15 minutes. Oh my god.
Hey, what's up?
I just want to make sure which one is this. Can I just see my cards and see if it's
Sure.
Did you get the email from the lady that can take my test?
Yeah, I did. Yeah. I mean, you should be able to see the verification too.
She
But...
said you have to like fill something out before I can make it.
Oh, really?
Yeah, she was saying like you have to fill out a form before they can like accept me to
Okay.
take it.
Let me. I guess I didn't notice that part. Sorry. Here, remind me where after this, and I'll do it. Yeah, this looks good. Yeah. Yeah. Yeah, it's all good. Okay, so let's do that thing real quick because I do not want to forget that. I think I have to do it per section, and I don't know if anybody has done it yet in this section.
I've never like done it in the testing center, then that's why you have to do it.
Okay,
So like you have to like accept that I can do it.
take it easy. Oh, another count. Testing request approved. Yeah, you're approved.
She said before.
I'll double check.
I can talk to them again. I guess like at home or tomorrow or something.
Here, let me check the actual site that has all that stuff.
Because I like requested a thing. And she was like, your teacher has to fill something out and then they'll, I don't know.
Yeah, I know that I did do it
Okay.
generically for somebody else, so it may be that they were telling you about that, but I know I did it for somebody else, so if it's, I think it's per class, but I could be wrong. Let me check.